Alright, in today's lesson we're going to look at differential rate laws. Most of the stuff that we look at in chemical kinetics is the rate law. The stuff that we looked at in the previous section on rates of reaction are important, and there are some questions that come up with that, but most of the time what you're going to be doing is you're going to be determining a rate law. And that's what I'm going to show you how we're going to calculate that. This is referred to as a differential rate law, and what differential rate laws are going to look at is concentrations versus rates, how the concentration affects the rate. Now, a rate law is a law just like we have in any other law that we see in science. It's just going to describe what's happening. It's not going to tell us why things are happening. It's just going to describe it. Okay, so how do we get to that? How do we figure out what the rate law is based on the experimental data? First of all, we need to talk about what's called an instantaneous rate. In the previous lesson, I talked about average rates. We would take a section from like 0 to 50 seconds. We would say, what's the average rate in that time interval? Now, it's not the actual rate because that rate is constantly changing. We would then look at the average rate from here, from 50 to 100, and so on throughout the entire reaction. But again, we want to know what it is at this point. What's the rate at this particular point? What's the rate at this particular point? What's the rate at this particular point? So to do that, what we do is we calculate what's known as an instantaneous rate by taking the slope of a tangent line to that particular point. Now this should sound familiar to you if you're in calculus. This would be your derivative. Alright, we're not going to actually do derivatives and calculate derivatives, but what it's going to do is it's going to give us the rate at that particular point in time in the experiment. Now, the only one that we're going to be concerned with is none of the other rates except for what's known as the initial rate, the rate right here at the very beginning of the reaction. So what we're going to do is the data that they're going to give you is going to be the instantaneous rate at time 0. So we're going to go back to time 0. How they do that is they calculate the rates and at various times, and then they extrapolate back to the 0 point. Alright, again, this isn't that important. They're never going to ask you to do these types of things or calculate them, but that is the origins of this thing called the initial rate of reaction. So what you're going to see is the data that you're going to be collecting is going to have initial rates of reaction. These are often used to figure out the order of reaction. It's going to come up quite a bit in this section. We're going to talk a lot about order of reactions. So we're looking at concentration effects, make a different color here, concentration effects on the rate. Right? You should know something about this, right? If you have a high concentration, the reaction tends to be fast, meaning you have a lot of stuff in the reacting chamber, so therefore it's going to react pretty quickly. Now, not every reaction is going to follow that rule, though. Okay, so we're going to have to look at that, and we can't just look at a reaction and figure that out. So the reaction rate is going to decrease as the concentration decreases, okay, for particular reactions. And that's the whole point, is what effect does the concentration have on the rate? We're going to use what's called the method of initial rates, sometimes known as the isolation method. I'm going to show you in another video a little bit more detailed calculations with method of initial rates. And we're going to do this at time 0 for various starting concentrations. So what the heck does this all mean? Let's take a look at an example. This is very typical of the data that you would see. Here's our reaction right here. What we want to know is what is the rate, or what effect do these concentrations have on the reaction, on the rate of the reaction. Does it make the reaction go faster or slower, or what effect does it have? Maybe it has no effect. All right, all depends on the particular reaction. There's no way I can look at this reaction and predict what's going to happen. Now, we deal with rate laws, by the way. We're focusing mostly, we're going to focus all the time on the reactants. We don't focus on the products because those aren't really important, because we're looking at how these reactants can make a reaction go faster or slower. All right, so let's take a look here. We've got first experiment. So this is experiment number 1. Experiment number 1, they take the concentration of the ammonium ion and the nitrogen, the nitrite ion, and they put them into a container. They let the reaction go, then they calculate the initial rate of reaction. Now, it's really important that when you're looking at, you're going to see data a lot for these. So when you're looking at the data, it's really important to recognize that you have concentrations versus rates. Concentration versus rate, that means differential rate law. So concentration versus rate, most likely initial rate because of the way we do these reactions. Okay, initial rate, that is going to be a differential rate law. Really important, because we're going to look at another one called integrated rate laws, which are going to look at two different things. It's not going to be concentration and rate. It's going to be something different. All right. They then do a second experiment. This isn't the same experiment like the other data we saw in the previous lesson. This is a totally different experiment. They now equalize the nope, I guess they don't, but they have 0.02, 0.2, and then we have the rate. 0.04, 0.2. Now take a look at what they're doing here. From here to here, concentrations of the nitrogen dioxide, or the nitrate ion, are constant. So therefore, this is why it's called the isolation method. By keeping this constant, what we can do is we can see if I take this reaction and I double it, right? I doubled the concentration. What happened to the concentration? Well, take a look. The concentration doubled. The rate doubled. So if I doubled my concentration, my rate doubled. By keeping this constant, I can see what effect this concentration has on this rate. I then do the next reaction. I go from 0.02 to 0.04. Again, I doubled the reaction. What happened to my rate? Again, my rate went through a doubling effect. All right, so we can be pretty confident that this, whatever I do to this, the rate is going to follow the same pattern, right? If I double this, it's going to double. If I tripled it, this should triple. All right, notice down here, I'll do this in a different color, that these reactions, or these concentrations, are all the same. And again, over here, what we're doing is we're going from here to here, we're going to double the reaction, and we can double the rate over here. So therefore, again, I can see, based on the data, again, I'm doubling, going up by, well, actually I'm not doubling it, but I'm going up by adding another 0.2 to it, and then I can see that this is going to go up by pretty much the same rate. If you want to look at this going up by 3, you say this goes up by 3 as well. Okay. Either way, if you look at the data, you look at the numbers, I'm going to show you a more systematic way of doing this. This is not an ideal way to do this. I don't want you guys doing this on a test or a quiz. I'm just purely talking about the concept right now. That you can see, hopefully, in this data that as this goes up and changes, this changes accordingly. This is referred to as direct proportionality. These two constants, or these two concentrations, are directly proportional to each other. So what we can do is we can write what's called the rate law. This right here is my rate law. What it does is it tells me what happens to my rate when I change these two concentrations. If this concentration goes up, if I were to double this concentration here, my rate when I did the calculation will double as well. If I double the concentration here, this rate would double as well. So these are referred to as differential rate laws, or more specifically just the rate law. We tend to drop the word differential out when we're talking about the basic general rate law here. So we write the rate law for a reaction as K, concentration of the reactants. And what we're going to do is we're looking at how these two are affecting the overall rate. All right. So let's take a look at the rate law in general. So here's our rate law. It shows basically how concentration is going to affect the rate, or the rate depends on concentration. This is your generic form. So this would be for reaction A plus B gives us like C plus D, some sort of generic reaction. All right, what we're doing is we're looking for M and N in these reactions. Okay. In the last one, M and N were 1s in the ammonium ion and the nitrate ion reaction that we just looked at. M and N, those are referred to as the order of reaction. And those orders of reactions are going to follow a 0, 1, or 2, which is known as 0th order, 1st order, and 2nd order. Okay, that's what these numbers M and N are. A and B are going to be your reactants. If you had 3 reactants, then you would have a C in here, but most typically you're going to have 2 or 1. K is referred to as the proportionality constant, or the rate constant in general terms. But technically it's a proportionality constant. This is a lowercase k. This is not capital K from equilibrium. There is a connection here, and I'll show you that a little bit later, but it's a lowercase k. So our rules for K are going to be a little bit different than before. All right, don't forget that the units here are molar per second. So we're going to have to figure out what the unit of K is, because it's going to correct and fix. That's why it's called a proportionality constant, and make these two things proportional to each other. Products are never written in the rate law, and we can only, again, very, very important that you follow this rule right here. You cannot figure out N and M, the orders of reaction, by looking at the balanced equation. You have to get this from experiment. Has to be from experiment. All right, so let's continue here just a little bit more. Our reaction order, okay, that's that M and N that I was talking about when we solve for M and N. Doesn't matter, you can call those variables whatever you want. We just typically call them M and N. But those are the orders. What are the orders? How are they related to each other? Well, if it's a first order reaction, which it was in that ammonium reaction, where we saw that ammonium ion and the nitrite, it's directly proportional. So that means that if my rate is, let's say rate is equal to K and we have a, and it's to the first power, then what that means is that whatever that happens to this is going to be affected the same way. I double this, this doubles. All right. Now, if my rate of is equal to k, or I'm sorry, to k times concentration of A, and it's a second order, that's what the 2 is. So n is a 2 as opposed to a 1. Well, if I double this, then this is going to go up by 4. If I triple this, this goes up by 9. So the rate is going to be affected as an exponential value, right? So we get an exponential change between them. And the third one that we typically see in this class, in AP Chem, is a to the 0 power, which means that the rate is not affected by a, that there's no effect at all. You're not going to be a change. So if you look at the data, you wouldn't see a change in the data as you double this, triple this, the rate would stay constant. Doesn't seem to make any sense. I get this was a little confusing, but it's, again, you have to use the data. All right, I'm going to show you systematically how to do this in another video lesson, but for right now I'm just giving you the background. All right, last thing we're going to talk about is the rate constant. All right, this K is different than the K that we saw in the past because this K is going to have units. All right, the lowercase k in kinetics has units. K for equilibrium, the capital K, no units, but that's not what we're talking about here. We're not talking about that. We're talking about lowercase k. All right, you are not only expected to know the units, but also the magnitude, the value of K. They typically ask you to figure this out. Now, if you want to, you can memorize this. It's kind of stupid to do that. You can actually, well, I think back some of you can do that. I just can't, and I get mad and I get angry, so that's why I say it's stupid. But it's not really stupid. Anyway, so what I would do is if I were to look for A and say this is a first order reaction, I would solve for this in K, and I would do rate over A, concentration, to the first power. What I would do then is I would substitute in the units, because you know what those units are for these, right? So this would be molar, this would be molar per second. These cancel out, therefore my unit is to the inverse second, which is what I have right here. All right, one more time. If I do rate is equal to K, A to the second power, what I would do is solve for K, and I would write rate, if I could write it properly, over A concentration squared. So therefore K is equal to, and again, this is just the unit. You would also then plug in the numbers. And again, I'll show you some calculations in class, and we'll look at this a little bit more. All right, molar inverse second over molar squared. This is going to cancel out. This cancels out. I have molar inverse seconds inverse. And there you go for those units. So you can quickly figure out the units just by solving for the rate constant. All right, so we'll look at more calculations. Like I said, there's another video lesson on how to calculate rates using what's known as the method of initial rates. So, thanks a lot.